Okay, please flip your desk back around this way and close up those Chromebooks. I'm going to show you something here, real cool. So we're gonna go through. I want to finish up showing you about the regression stuff. There's a very short assignment. This won't take you long, but it's a really important thing to know. So we're gonna do. I want to see your buttons and stuff too. All that's away for now. We're gonna have a little conversation and then you can work. So we're gonna do to split up the tests rather than have them. I think it's better if we kind of take them as we go a little bit, right? So we're gonna do a test over everything we've covered in Unit 2. Then regression is gonna be the last thing. So I will put up a non-graded practice test. You don't have to do it. I'll put something up there if you want to use it, just like before. Optional if you want to use it to help prepare. But we'll plan on doing the test like sooner than later. Okay, like I'm thinking, like maybe even no later than Wednesday, Tuesday or Wednesday. Right? And there's not that much to do. I mean, this is all written stuff. Shouldn't be a big deal. Okay, so wrap up your homeworks. This regression one, I think it's only like 5 problems. It's really short. It would probably only take you 10 minutes to do. But I want to show you how to do it. Okay. Questions on that? Okay, good. All right, so here's where we kind of started with things yesterday. Now, regression is a technology thing, right? There's an algorithm that the graphing utility is going to use, whether it's a graphing calculator or Desmos, and it's always going to be the same. It's always going to be the same. So when we put in this data, we're always going to get back the same regression model, right? Remember how to do that. Well, we're going to do another example, so you'll have a chance to tell me. But we're going to create it just real briefly. We're going to create a table in Desmos. We're going to do this in Desmos. And we're going to populate the table with the input values and the output values. And then all we have to do is then once we do that, it's going to spit out a value for M and for B for our regressional model that are going to be the slope and the y-intercept of the best fit line based on that data, right? And so then if I want to actually do something with that, all I've got to do is I can create a line and do something with that also. Now, we didn't get that far yesterday, but I'm going to show you that today. What we found yesterday was this is a slope of, rounded to 2 decimal places, 0.18 is the slope of the best fit line, and 5.75 is the y-intercept of the best fit line. So what do those represent? Instead of y, our output is a capital P, and of t if we want to write it in function notation, right? So that's equivalent to y, and instead of an x, our input is a t. So instead of y equals mx plus b, we've got p equals mt plus b, right? But that's our model, okay? Questions? Okay, now I'm going to have you work with me on this next one. Here's the. Okay, I thought I had another one. Here, let me pull up a sample one. Yeah, I thought I had one on there. Hey, I got one for you, real quick. Well, what's it mean if the slope is? I'll hold off on that for a second. Never mind. I'll ask you that question in a second. Okay, there's the next question. Okay, let me take a picture of this and you can read it and get familiar with it, and we'll talk about this. All right. So they tell us an Uber ride costs $3.20. Oh, that's the wrong one. That's totally the wrong one. What am I doing? Pulled up the wrong question, all right? There it is. Whoops. That's what I wanted. Did we do the movie ticket yesterday?
Yeah.
Okay, let's do something different. We'll do this one.
When you graph feed, it's like, what is it gonna be like on this thing? You just enter, X equals whatever date.
Okay. Okay, so then, so here, look what they're doing. They're giving us an object speed is recorded at various time intervals, right? So we're recording an object speed after 1 second, 5 seconds, 6 seconds, 11 seconds, 4, etc., right? And we're taking some data, and we're going to assume that the data is not, like any data, is not perfect. There's going to be some error in the data, right? But this is what we got. We want to find a regressional model here, a best fit line, and we want to actually use it this time. We're not just going to find it, but why do we have a regressional model? Because we need to use it, and we use it to make a prediction. That's the whole point of a mathematical model, is we want to predict an outcome. Okay, we want to predict the outcome for the velocity when t equals 8 seconds. Okay, and we'll round our answer to 2 places. So now, you can work with me on this. Talk me through this here. What am I going to do with Desmos to make this work?
We're gonna enter all of the data into a graph.
Okay, so the first things first, we're going to,
Create a graph.
yeah, we got to create a data table, don't we? Okay, and I guess I can scoot up here. We just need to put the data in for now. So where do I go to do that in Desmos? I hit plus and I choose table. Okay, and so for this one, instead of x, what's our input? T. Okay, and what's our output? V, or velocity. Whoops. Okay, and then we're just going to put all the data in. So, and you can do this with me. So 1, 5, 6, 11, 14, if you want to. You don't have to. 15, 20. Okay, and then we'll just put in all of the corresponding velocity data. So 3.0, I can just put in 3. 15.2, 18.7, oops, that's going to throw it off a little bit, isn't it? 0.7, 39.4, 34.5, 43.8, and 71.3. Okay? So I got all my stuff in there. Now we want to get the model. So what do I do to get the model?
T.
Okay, so it would be, we want to do it in the form y equals mx plus b, but it's not a y.
It's a V.
It's a v. So we're going to do v1, and instead of equals, what do I do? Tilde. Okay, so that's our indicator that we want a model, right? We're going to let Desmos build a model for us. So v1 equals y equals mx plus b, so it'd be m times t1 plus b, right? And it gives it to us. So there, that's pretty cool. It gives us, and I'm going to change the color of this thing so it's not black, so it shows up a little better. Let's make it red. Okay. So there's what we get right now. Now let's talk about what this stuff means for a second. So we can look at the distribution too, right? I want to zoom out to see this whole thing, right? If I zoom out a little bit, I can start to see all those data points collecting, and it looks like they're right there. Now, it's nice when we're looking at data, when we're doing statistical math, it's always helpful to try to maximize the spread on whatever screen you're looking at, right? So I've got a lot of wasted space in the on the x-axis, right? I don't need all that dead space, the negative numbers, and I've got a bunch of positive numbers that are too big. I can look at this and see that my input values, my t values, range from 1 to 20. So what's nice to do then is to go up to the graph settings, and we'll just choose graph settings that match our data, right? So we could go, how about if we go from negative 2 to like 22. And watch how much nicer this looks if I do that. Okay, that's going to spread the x values out. What about the y values? What could our minimum there be? It's nice to like make it, you want to see the x-axis, so we'll go a little bit below. But like, I don't know, like what do you think, like -5 or -10 or something? Let's do -10. Up to positive like 80 maybe. And look how nice that looks then. Right now we're starting to get, that stuff's in the way a little bit, isn't it? I could do this though. Why don't I do?
Oh, that's what I'm doing.
Yeah, that's kind of a pain that stuff's in the way like that. Uh-oh, I want to do that. Go back. Oh, I just messed it up. Darn it anyway. Can I not go back? Oh, there we go. I want to tweak that just a little bit, don't I? Because those little buttons are in the way. That's kind of a design flaw, isn't it? So let's make the top be something like 25. That's better. Now I can see everything. Okay, I want you to notice something here. The red line is the line of best fit. Does it actually go through any of those points? I mean, it's close, but it looks like it's really close to that one, but it's a little bit off center, right? But it doesn't go through any of them perfectly. We mentioned that yesterday, but it's the best line for the distribution, right? Anytime you're taking real world data, how likely is it going to be that your data is, even if it's supposed to be linear, how likely is it going to be that it's ever going to fall perfectly on a line? Everybody click those close. This is something, I really want you to hear this. This is really cool stuff. How likely is it going to be that your data is ever going to be perfectly on the line? Not very. And think in terms of a scientist now. Why is that?
Because it's the approximate of everything.
There's a ton of error, right? Every time we measure something, no matter how good the lab is, there's always going to be some error associated with it, right? And there's going to be some irregularities just in the environment where the experiment's done too, probably, right? But on average, what's going to happen to that error? If I have a whole bunch of data points, what can you tell me about the error I'm going to get with each individual data point? They're going to average out, right? On average, I'm going to get just as many errors above where it should be as below where it should be, right? And the more data points I have, the better the technology is able to take the data and average out that error, right? And so, for example, I'll give you a quick example. This is kind of a statistical thing, but it doesn't really have a lot of bearing on what we're doing right now in math, but it's really important to talk about this stuff. Would you be surprised if I had everybody in here flip a quarter 10 times? Would you be surprised if somebody, maybe one person maybe got 10 heads and no tails? I mean, it might happen, right? But you certainly, even if that didn't happen, you'd get some people that had 8 of one and 2 of another. And there'd be some people in the class that would be deviate from the average of 5 and 5, right? Everybody agree? So you wouldn't be surprising if you had 80% heads and 20% tails. Now, if I gave somebody an assignment to flip a quarter 1,000,000 times throughout, keep track of it throughout the course of the rest of the year and diligently keep track of that, would you be surprised if the result ended up being 80% heads and 20% tails? It could never happen. It would never, ever happen. I mean, if you wanted to wait for that to happen, you would have to wait a trillion times the age of the universe, and it still wouldn't happen. It'll never happen. In a million statistical, if they're 50-50 odds, it's statistically impossible. The odds are so slight as to be, it could never happen. Vanishingly small, right? How come? Because the more data you have, the more there's going to be a tendency for the error to average out, right? For a very small sample, it doesn't have to be that way. If I flip a coin twice, I could easily get 2 heads and no tails, right? If I flip it 1,000,000 times, I'm going to get 50% and 50%. Does it mean I'm going to get exactly 500,000 heads and 500,000 tails? No. It might be off by 8 or 10 or 20, but what's 8 or 10 or 20 out of 1,000,000? Very small percentage, right? See my point? Okay? So that's the same kind of thing we have going on here when we take data to come up with a linear model like this. The more data points we have, the better it is. Well, how do we know how good it is? Desmos tells us, is the answer to that. If we look down here at our answers, what stuff does it give us? It gives us M and B, which we'll talk more about. That's really important. But it also gives us some statistical information here, right? It tells us that R squared equals 0.9374 and R equals 0.9682. Okay? The R is not so important in a way. We'll look at a couple different examples where, well, actually we probably won't today, but the R could be positive or negative. It's positive if the slope is increasing, it's negative if the slope is decreasing. But R squared is always going to be positive, right? This is what we call the strength of the correlation. And here's a way to think about it. Now, don't take this literally, because this is not true literally, but this is a really good rule of thumb. If I want to know how good is this model fitting my data, I look at R squared. And you can think about it as kind of a percentage. We could say, and once again, this is not strictly what it means, but it's a good way to kind of think about it, gauge what this means. If I wrote the decimal 0.9374 as a percentage, that would just be about 93.7%, right? So we could kind of say that, yeah, this data is pretty linear. It lines up fairly linearly. We could say it's got roughly about a 93.7% adherence to the model. So it fits the model about that well. Now, if I added a bunch more data points to this, what do you think is going to happen to that R squared? It's going to go up a lot, right? If I just have a few points and they don't line up in a very good line, and the slope is not very steep, then you're going to end up with an R squared that's really low. And you know then, what's your confidence in any prediction you're going to make from that model? If R squared is low, could you confidently predict that this model is going to give you a good outcome? Not so much, right? The strength of the correlation wouldn't be very good, right? Now, if the R squared is really high, and with good correlation, like it wouldn't be absurd if we had, say, 50 data points and they fit fairly linearly, I would say that the R squared would probably be something like 0.997 or 0.998 or something. Very good, very close to 100%, right? What would happen if all the data points exactly fit on a line? What would R squared be? 100%, it'd be 1.0. They would perfectly fit the model in that case. Does that give you an idea? So this is just a basis of comparison, right? Okay, one other little, we're not going to spend it, I mean, we'll talk more about this at the end of the year, but I want to just, now's a good time to talk about it a little bit. Would you say that describe this correlation among the green data points? Is it positive, negative, or is there no correlation? What do you think? Positive, good. So you've talked about this. Why is it positive? Because it's a positive slope. So what's that mean? As t increases, y also increases. Well, v in this case, v also increases. That's a positive correlation. If the input variable is increasing and the output variable is increasing, that's positive. So what would it look like if it were negative correlation? It would go down, right? So as the input variable increased, the output variable would decrease. How would you get something that was essentially no correlation?
It'd be everywhere.
It'd be everywhere, and what would the slope of the line be?
Flat.
It'd be flat. And think why that would be. If I had a flat regression line, does the value of t have any impact on v?
No.
No. Very little impact, right? The value of v is going to stay the same no matter what. If the steeper the slope gets, the stronger the relationship is between the input and the output variable, right? If the slope is steep, there's a pretty big relationship. As I increase t, v is increasing pretty dramatically, right? The shallower the slope, the weaker the correlation. Does that stuff make sense? Just file it away for later. So, I mean, I could show you a couple. This is probably overkill. I doubt you guys really even need me to do this, but if I threw up a couple quick, let's see, I'll do that. So, what's that? Negative correlation. What's that? What's that? I mean, that's no correlation essentially, right? There's very, very weak correlation there, right? That would be an example of no correlation. There's almost no line there, and even if there were, it's not, the data's so spread out. Does that make sense?
Yeah.
That would be the best choice. There would be no correlation. Okay. All right. Okay, so let's keep going with this then. Was that our? Oh, that wasn't it. Oh my God, I've got it written down here. That's all we need, right? Didn't I put it on here somewhere? There it is. Okay, good. Yeah. Question.
So on this, so it's negative, positive,
Yeah, so normal, that's just that's a crazy answer. I just wanted to keep you honest. There's no answer's gonna be normal. There's no such thing as normal correlation. Yeah. I just threw that out there so you don't get lazy, don't get complacent. Right, you gotta think about it. Not so much for you guys, but for the other classes. So now let's use this thing, right? So how could we use this model to make a prediction? Because after all, that's what we wanted to do. We wanted to predict the velocity when the time equals 8, okay? So here's how we can do that. We can come down here and go to a new row in Desmos, and we can use the M and the B to write a function. Like I could even do something like now, I could write, let's do V of t. I wonder if I can do that. I maybe just have to use V. I'm not sure about that. I think I have to use, we'll try it. What's the worst thing that can happen? It doesn't work. So V of t equals mt plus b. No, it worked. Look at that. I want a different color though, so I can distinguish those two. What do you want it to be? What do you want? Maddie, what do you want? Okay, or Katie, what do you want? Purple? Is that good? Okay. Okay. Purple works. So there's our purple graph. Notice the purple graph lines up perfectly with the red graph, right? But the purple graph is useful because it's a function. So I wrote it in function notation. So if I want to evaluate this at a time of 8, what would I do? Okay. I'm going to input an input value of t that's equal to 8. So I would just do V of 8, and look what it predicts. How about that? How about that? Okay, so that's making a prediction for us. Now, so the prediction is when time equals 8, the best guess for the velocity is 24 point, rounded to like one place or two places, 24.75, right? Okay. That's the best guess. Is it guaranteed to be that? No, if we measure it, there's probably some error in the measurement, and maybe it oscillates around an average value a little bit. But that's going to be our very best guess. We're most likely to be correct or nearly correct if we pick that value. I got one for you. What are the coordinates that data point right there, I can click on it. So one of our data points was when t equals 20, we measured a velocity of 71.3. Is that my best guess for what the velocity would actually be if I wanted to make a prediction? No, it's not actually. Even though isn't that weird? Even though that's the measured value I got, the best predictor would be, I'm just going to, there it is right there. How about that?
There it is.
The best estimate is 64.25. How about that? Because that's what the model predicts. The model is more powerful than any individual data point at making a prediction. Okay? What else? Okay, so here's the other thing. So I want you to notice that, would I be mistaken if I went back to our last example? I want you to point out the flaw in my reasoning here. So in this case, it asked me to write down the regressional model, and it wanted me to round, did it say something like that? Okay, that's...
Well, there it says round to the nearest cent.
Yeah, okay, the problem yesterday, I forgot it was this kind. The other type of question, this one actually asked for a prediction. But the other kind of question that you could get is one where it just says, write out the regressional model and round all of the coefficients to the nearest hundredth, I think, to 2 decimal places. So this is the model. If the question asked you that, if it asked you to write down the model with rounded coefficients, this would be the correct answer, right? Would this be a good model to use to make a prediction?
Yeah.
It wouldn't be bad, but what's going to make this a little bit less accurate as a predictor of outcomes than, for example, the one that we had right here?
It's rounded.
Oops. Where is
It's not
that?
exact.
Where is that? Oh, it's over here. Whoops. Now look at this model. This model, look at the values of M and B. M is 3.29143, and honestly it keeps going. It just shows you that many points, but it's taking it out to like 12 places. Which one's going to be a better predictor if I use the unrounded values of the parameters or I round them? Unrounded for sure, right? And when we do something like this down here, when I use the M and the B to create a model, I'm using the unrounded, hugely accurate values of M and B. Make sense? Okay? So last one then. So now what if I went one step further? So we got our answer. Now what if we go one step further with that? And actually that's the one that we started yesterday, now that I think about it. What if we wanted to do, no, that's not what I want. I'm pretty proud of this next one. These are pretty good. You're gonna like these. So what about one like this? Okay, another movie ticket one. They're giving us data. Input data is the year, the output data is the average movie price. Now, how do you think I could use technology to answer this? Rounded to 2 decimal places. The linear regression model predicts, oh, that's not the one. Darn it. Oh my goodness. Line model. Okay, I don't have the wording right. I'll fix it, but I haven't made the assignment live yet. But here's what it's going to say. It's going to change it a little bit. It's going to ask you instead, it's going to say something like, predict the year when the movie price first becomes $40. Or something. How could I do that?
When you go to your graphing, you could do T equals whatever you want it to be.
Okay. So let's go back to the last, we could do this with our last example. What if we wanted to use this model, and let's say we want to arbitrarily find out, this is a velocity question. We want to know at what time is the velocity
800.
going to first cross, a value, big value, like 800, based on this model. Now, do you think it's more accurate to make an estimate, use the model within the data? That's called interpolation, right? We interpolate when it's within the set of data, or when we extrapolate. Extra means outside of, right? When we're picking a value that's outside of the data. Which one do you think is going to be probably a more accurate prediction?
Extrapolate.
Extrapolating is less accurate because any little, now think about this, any little tiny error in our line, and there's some error, right? It's pretty accurate, but any little bit of error is going to get magnified the further we go away, right? Think about any slight variation in a line. You could slightly tweak a line, like with a laser beam, but that laser beam, if I move it through a very small angle, and it's shining on a building that's 3 miles away, it's going to move quite a bit on the building, isn't it? Right? So any slight variation gets magnified when you go far away from the data points. So interpolations are inherently more accurate than extrapolations, right? But let's make an extrapolation. Let's say we want to find out how many seconds will it take for this thing, theoretically, based on our model, to reach a velocity of, in what second? I don't care the exact value, I want to know in what second. So if it's 1.2, it's going to be in, we'll say it's in the first second, right? Does that make sense? Yeah, see what I'm getting at? Okay, so how could we do that? How could we do that? I think, Jim, what were you saying? You had a good idea.
You said the y-axis equal to the value you want.
Okay, so I could do something like y equals 800. And if I zoom way out here, look what happens. There is a line, a horizontal line at y equals 800. So if I click on that point right there, that's the notice that the y coordinate of my model is 800. So this is the very first time, theoretically, that our model is going to predict that our velocity is going to reach a value of 800. Right? Does that make sense? Okay. So this time we're not inputting a value into the function. We're setting the line equal to a number and solving for x by just finding the x coordinate of the intersection. That make sense? Okay? All right. So now the question I'm going to ask you, think about this a little bit. Let's just pretend that these are movie prices. And we wanted to figure out in what year is the movie price first going to hit $800, and these are years from today, I guess, or something, right? So is it gonna be the 243rd year or the 244th year?
43rd.
43rd, right? It's gonna be the 200, somewhere in that 243rd year, right? So whatever year that is, 2000 and whatever, right? It's gonna be, somewhere in that year, that's when it's gonna first hit $800, if we're talking movie prices. Make sense? Okay, I think you got it. I'm gonna let you go. So I gotta put that other question up. You can work. Go ahead and break out, how much time we got?
6 minutes.
Oh, we get a couple questions answered in 6 minutes,
Tell
maybe.
me that's a year.